In this video, I have prepared a pure data project to give a practical demonstration of sampling and quantizing, two fundamental aspects of digital audio related to the signal conversion. Any signal needs to be converted either when it comes into or out from a computer, and the analog to digital conversion, the process we may see on the image below on the left side, consists of three different processes the signal is subject to: an analog low-pass filter, a sampling process that provides a set of samples from the signal, and a quantizing process where we generate discrete numbers for each sample. The final goal is to convey a continuous function in time of real numbers to sequences of samples read at a given sampling rate. The opposite process, the digital to analog conversion, takes sequences of samples and converts them into voltage and eventually in audio. And now let's delve into details of sampling and quantizing. In this window, I can synthesize a sine wave in the yellow panel and simulate a sampling process in the gray panel by the use of a snapshot. Let's start with a 8 Hz sampling frequency and let's start generating our sequence. When the signal frequency is lower than half of the sampling frequency, the resulting sequence can recreate the original frequency without any problem. We can also compute the number of samples needed for a single period of a periodic signal by the fraction between the sampling frequency and the signal frequency. If the result is an integer, we have a finite number of samples for one single period, and if the result is a rational number that is not an integer, we have a finite number of samples for a multiple of one single period. For example, let's choose 0.8 Hz for the signal frequency, and we obtain a sequence of samples made by 10 samples per period. If I choose 1 Hz, we observe 8 samples per period, and for 2 Hz we observe 4 samples per period. When I match the half of the sampling frequency, that is called the Nyquist frequency, we have only 2 samples per period. This is the highest frequency we can observe in our signal. In fact, when I exceed this frequency, the result is a folding back. This is called aliasing, and the alias frequency is computed by the difference between the next multiple of the sampling frequency above the signal frequency and the signal frequency itself. For example, if I choose 7 Hz for our signal, the result is a sequence of samples that have 8 samples per period. The aliasing is a cyclical phenomenon. In fact, each time I match the sampling frequency, I obtain a constant sequence of samples, and when I exceed this frequency, a new inversion starts again. A final thought about the sampling process is the use of the oversampling in effects like compressors or saturators, and it allows us to perform our processing by getting rid of the aliasing in the audible range. The next example is a tiny review of the binary representation. But why do we need to deal here with the binary representation? Because the signal amplitude is represented by a finite number of bits, and we need a high number of bits if we want to represent our amplitude in a precise way. For example, with only one bit, we can only choose one single value among two different values, 1 and 0. With 2 bits, we can represent one of 4 different values from 0 to 3. And we need 3 bits to represent one of 8 different values from 0 to 7. And so on. For example, if we want to represent one of 128 different values, we need 7 bits. The following example will use 16-bit signals, which can represent at maximum 65,536 values. And now let's move to the auditory domain and hear what different levels of quantization sound like, and also review some notions about the sampling process. In this window, I can synthesize a sine wave and I can control its amplitude and frequency on the top of the window. On the middle part, there is the corresponding frequency analysis, and on the bottom part, there is the waveform. Let's start with a 16-bit signal. We can see the waveform and the resulting band of spectrum excitation, and also we can hear the sound. When I increase the frequency below the Nyquist frequency, the corresponding spectrum excitation is increasing, but when I exceed the Nyquist frequency, the result is a folding back. I have prepared also a frequency swipe from 0 to 44,100, our sampling frequency, and we will see that while the computed frequency will run from 0 to 44,100, the resulting sound and signal will run from 0 to 22,050 Hz and then back to 0. We can see the same phenomenon with an oversampling and anti-aliasing filter, and we will see in this case that most of the aliasing will be filtered out. By using the maximum amplitude in a 16-bit signal, our curve is drawn by 65,536 points, like we were seeing before. But when I lower the number of bits, our curve is drawn by less points. As a consequence, I am creating a step function from the original smooth signal with the flattening of the peaks. This process generates some noise and some harmonics that are added to the spectrum. If I change the frequency of the signal, we can see the resulting spectrum and the timbre that is changing as well, because there are some conflicting harmonics that add up or cancel each other out. This effect can be reduced if I turn on the anti-aliasing filter. We can see the noise is reduced with the anti-aliasing filter. We can change the timbre also by holding a fixed frequency and changing the number of bits. For example, here, let's start with 8 bits and reduce the quantization level. We see that the signal formants are increasing or decreasing according to the quantization level. You can see the same effect without the anti-aliasing filter. When I reach the minimum quantization level, I generate a square wave with a DC offset, and this is the typical sound of some old-style digital synthesizers like those used in some retro games. And now we can also hear the sound. This was the last example of this video. I hope you enjoyed. See you next time.